Chapter 15. Chapter 15 is on nebula, spectroscopy, and Cepheid variable stars. So the telescope, when we use a telescope to look at a star, it can tell us the apparent brightness of the star, okay, how bright the star looks to us. And another thing we'll notice through a telescope is the color of a star. If you can measure the star's parallax, then that can give the distance of the star. And so if you know the distance and the apparent brightness of the star, that will give you a clue to its true brightness, its luminosity. For example, if you see two stars, they both appear equally bright in the sky, but your parallax measurements tell you that this one is much closer and this one is much further away, then this one must be much brighter, because if it's further away but it looks the same as this one, it must have much greater luminosity. Okay, so those things you can learn with the telescope if you can measure parallax. If you can find what are called binary stars, two stars in orbit around each other, they can be observed to be in elliptical orbits. That indicates that they obey Kepler's laws and therefore Newtonian physics, just like things in the solar system. You can observe that some stars vary in brightness. But if you map out the stars, you look at all the stars we can see in the sky, either with the eye or with the telescope, you typically will find that it appears as though the sun is near the center of a big accumulation of stars, which we might call a galaxy. So along with stars, there's these fuzzy looking things in the sky that were called nebula. Nebula just means like little clouds. All of these things are too far away to measure via parallax. So if you don't know how far away something is, then you also, when you look at it and see how large it looks, you can't figure out how big it really is. Because if it's close, or at least closer, then it's going to be smaller, and if it's further, it's going to be larger in size. So to start answering these questions, answers to those questions kind of had to wait until some new discoveries in science. One of those discoveries is the idea that light is composed of many wavelengths or frequencies. This is the Roy G. Biv, the red, orange, yellow, green, blue, indigo, violet, the colors of the spectrum. Light varies. The red has long wavelengths and low frequencies. Violet has short wavelengths and high frequencies. Another thing that was discovered was that the different types of objects give off different sorts of spectrum. So, for example, gaseous objects are found to give off what are called a line spectrum, which is they give off distinct, separate colors. Okay, it's not a rainbow of colors. Gaseous objects give off these, like a certain particular color of red, a certain particular color of green, a certain maybe 2 or 3 shades of blue. Okay, and that those objects those color sets are distinct to a particular material. So hydrogen has a very particular set of colors, or a fingerprint of colors. Oxygen has a different fingerprint of colors. By contrast, hot, dense objects, for example, glowing, red hot metal, red hot iron, gives off a continuous spectrum. That is the Roy G. Biv spectrum. When you look at them, because of the way they give off their colors, things that are hot the hotter you make them, so they go through a very distinct selection of colors. So if something's not that hot, if you're heating up a piece of metal, it's not that hot, it may give off heat, but it doesn't glow. You heat it up more, it starts glowing red. Heat it up more still, it gets brighter, it's glowing orange. Heat it up more still, it'll get yellow and be glowing very bright. Heat it further, it glows white. If you could heat it even further still, there's basically not much on Earth that can handle this kind of heat, but it would actually get up to glow bluish white. Okay, so red it's all hot, okay, but red is something that is glowing and is dense and is the coolest, whereas blue-white is the hottest. The Doppler effect, that's another discovery. The Doppler effect was that the frequency of a wave, that includes light or sound, is shifted depending on whether the object is coming toward you or away from you. This is things if you've ever been sitting at a stoplight and heard an ambulance go by, or a train, or somebody with a boom car with a heavy bass, you've heard this effect. You've heard the frequency change as the ambulance or the train or the boom car goes past you. Another key discovery was photography, the ability to make a photographic record through a telescope. Right? So, what are some of the specific things that were discovered using these new techniques? First of all, if you took the light of a star and ran it through a spectroscope to create a spectrum, it was found that stars have continuous spectra. In other words, the spectrum of a star and the spectrum of a glowing, red hot or orange hot or yellow hot piece of metal are very similar. Okay, so this tells us stars are incandescent objects. They are dense and they are hot, and they put off light because of the fact that they are dense and hot. Okay, they're glowing. Some of the nebula that were investigated were revealed to have a line spectrum. That would indicate that the nebula are gaseous and not dense. But some of the nebula, in particular the ones that had a sort of spiral form to them, called spiral nebula, produced continuous spectrum like stars. That would suggest that they were full of stars or star-like in some way. All right. The first good photograph of a spiral nebula was taken in 1888, and when they took that photo, the conclusion was, now we know what spiral nebula are. They are forming stars, forming solar systems, because it showed you could see more of the spiral pattern, and the idea was, there's this bright area in the center, and that was where the material was coming together to form a star, and then there's this swirl around it, and that would be like the part that's going to form into the planets of the solar system. So the first photographic images of spiral nebula were taken as evidence that these were forming solar systems, and therefore not that far away. Okay, they were out there, among the stars. But by the time you get to the 1920s, there were a lot of people who were arguing that no, the spiral nebula were whole other conglomerations of stars that were not even part of our galaxy. So you can see there's two wildly different interpretations of what the spiral nebula were. Either like a forming star system, or which is relatively close, relatively small, or they were a whole other galaxy, in which case they were extremely far away and extremely large. Which is what are they? That was the question. And to be able to figure this out definitively, we needed to be able to measure the distances to stars or to these nebula, and that couldn't be done with parallax. All these things were too far away to measure with parallax. So the solution came through a person named Henrietta Leavitt, who worked at the Harvard Observatory in Massachusetts. And Leavitt discovered how to use something called a Cepheid variable star to measure distances in space. Cepheid variable stars get brighter and dimmer and brighter and dimmer. And Leavitt, by studying a kind of a small galaxy called the Magellanic Cloud, there's two Magellanic Clouds, the large Magellanic and small Magellanic Clouds in the southern sky down. You have to be in the southern hemisphere to see them. By looking at variable stars in those, she knew, first of all, she was looking at a grouping of stars that are all kind of the same distance from Earth, and she began noticing that the variable stars that were brighter had a longer period. In other words, the time to go from dim to bright and then back to dim again was long, whereas the dimmer variable stars went bright and dimmed down more quickly, bright, dimmed down more quickly. So she realized there was a relationship between the period of the variable star, how long it took to go through its cycle, and the luminosity of the variable star, what its output was. So this Cepheid variable period luminosity relationship that Henrietta Leavitt discovered provided a way to measure distances in the universe. Cepheid variable stars were very bright. They are very bright stars, so they can be seen from a long way away. So the way you measure a distance using Henrietta Leavitt's method is you might look at two nebula, and let's say you see two nebula, and they each have a Cepheid variable star in them. Then one of those Cepheid variable stars has a 10-day period, and one has a 2-day period. Okay, well, the 10-day period indicates a more powerful, more luminous star than the 2-day period. So if those two nebula, let's say that their variable stars each look the same brightness, the same apparent brightness as we see it, well, okay, that would mean that the one with the 2-day period had to be a whole lot closer, and the one with the 10-day period had to be a whole lot further away. Because if they look the same, we know the 10-day is the brighter one, so in order for them to look the same, the 10-day has to be further away, the 2-day has to be closer, so that the distance difference cancels out the brightness difference. Okay, that's the basic idea behind using a Cepheid variable star to measure distance. This is one of the Henrietta Leavitt's discovery of the period luminosity relationship of variable stars. It brought about what astronomers call the use of standard candles. A variable star is a standard candle. It's something who you know something about its brightness already, and you can use that to measure distance. And this is one of the big discoveries in astronomy, really kind of since Galileo and people like that. This is what allows us to know how big things are in the universe today. A huge breakthrough. And Henrietta Leavitt was not like a big astronomer. She was actually hired to do grunt work at the Harvard Observatory. So her story is a very interesting one. So that's the gist of it for chapter 15.